Hello, let's go ahead and get started today. It's nice weather out, so hopefully get out and walk around and enjoy it a little bit. But today we're going to continue with some TCPIP programming topics. And today, specifically, we're going to talk about HTTP, which is essentially the protocol that sits on top of TCPIP that allows the web to exist. So in other words, when you go to a web browser, you put in a URL or click on a link. HTTP is the protocol that is responsible for requesting the page and then getting the page content and showing it in the browser. The browser is responsible for rendering it, but HTTP is the part that's responsible for the request and the response. And all of that sits on top of TCPIP. All right, so let's take a look. So TCPIP, as we talked about previously, was kind of the foundational protocol of the internet. And so it should come as no surprise that web pages, web browsers are built on top of TCPIP. So web browsers, web servers use a protocol that sits on top of TCPIP. It uses the transport services of TCP. In other words, the ability of TCP to sequence and reliably exchange data in a session. It uses that. And then it uses the address and routing services of IP to send and receive pages or a request to a web server, and then the web server then will respond and give the stuff back. So the packets themselves or the datagrams themselves are all TCP/IP datagrams. So today we're going to look at that protocol from both the client side and the server side, and we're going to look at how you could actually create your own web server. All right, so to start out here, HTTP stands for Hypertext Transfer Protocol. There have been several versions, 1.0, 1.1, 2.0. The major differences between those, it's largely the same as it was with version 1.0, and most servers are backwards compatible and will still support version 1.0. But essentially the main difference is that version 1.0 had to have a different connection for every request and response. In other words, if you went to a web page and that web page had, let's say, pictures on it, and you would have to connect, get the HTML that then had the picture links, and then you'd have to open a separate connection, get picture number 1, open another connection, get picture number 2, and so forth. And then they realized that that was inefficient, and so they made it so that you could open a connection once and then request the page and then request this picture and that one or whatever, request multiple items with having one connection open. So the difference between those would be like making a phone call. And if you make a phone call to like tech support, version 1.0 here would be like you're allowed to ask one question, and after they answer the one question, they hang up on you. And then you're like, oh crap, I had another question, you have to call back. So version 1.1 allowed you to essentially ask multiple questions on one phone call. And version 2 added this kind of binary framing layer and ability to do multiplexed communication through that. The binary framing layer can be more efficient at transferring data, and the multiplexed communication can allow you to be retrieving more than one data item essentially concurrently or at the same time through the one connection. It allows you to multiplex that. So rather than having to get image 1, image 2, image 3, you could actually be getting multiple things at one time. It's still a single stream of data coming in, but it has this ability to multiplex that. Okay, so how does it work? So let's dig in and take a look at how HTTP actually works. So the idea here is it's based on a client-server architecture. In other words, just like we've done in the past, you have a server that's listening on a port for incoming connections. Usually that port is HTTP port 80, HTTPS, which is the kind of secure socket version of HTTP, is 443. But really any port is possible. You could use, just like when we wrote our example TCP/IP code for the last lab, you listened on maybe port hex 1234. You could actually have a web server sit on port 1234. And maybe you've heard people talk about the dark web. That's usually things that are HTTP services but are running on some unknown port that somebody would have to know that port in order to connect to it rather than the standard port like 80. And main thing about the port is the server just has to be listening on it, has to be listening for that incoming connection. And the sequence goes like this. The server will be listening for an incoming connection. They will accept the connection. A request will come in. And then the server will send a response back. And then the client, which would be like your web browser, that's what initiates the connection to some server. And then the sequence there is once the connection is made, the client sends a request and then receives the response from the server. So it's a very simple transactional model where connection is made, make a request, get a response. Or on the server side, accept the connection, receive the request, send the response. And then at that point, if it's HTTP version 1.0, then you close the connection. If it was one of the later ones, then you could keep the connection over and get another request and send a response, or get another one and send a response, and so forth. Okay, now let's take a, since the requests and responses are an integral part of this, let's take a little closer look at those, a little deeper dive into what those look like. And the request and response are similar in their format and their structure, and they're also designed to be human readable. In other words, they're text-based. Now, that is important because that means we don't have to worry about like binary formatting of the requests and the response headers. We don't have to worry about some weird structure and Indianness. It's really just text. So you could, in theory, connect to a web server using a raw telnet session that makes a connection, and you could just type in characters and get a response from the server directly. Now, before we dig into the details of what the request header looks like and what the response header looks like, or the request and response formats, what those look like, they both have a format that looks like this. They have an initial line, they have 0 or more header lines, and then they have a blank line by itself, carriage return line feed on basically an empty line by itself, and then they have the message body, which is optional. Sometimes there isn't a message body, sometimes there is. But you'll notice that they all have this format. So initial line, additional possible header lines, and then what separates the header from the message body is this blank line by itself. So let's go through and look at requests and responses, their individual formats directly ourselves. And let's start with requests. So here's what a request looks like. So the initial line would look like this. A method, a path, and then the version. And notice it's separated by spaces. There's a space there. So a typical line would be get, and then some path to some resource, and that could be a HTML file or whatever, but it's some sort of, maybe I should change that so it says HTML instead of HTTP, but this is, I'm just going to make that say HTML and make it a little more clear. All right. But the idea here is this is just a path to some file. So you'll notice that when you go to a web page, it'll have some path that could be just the default to some server, like for example, google.com or shawnee.edu. And then this is the version of the request type that we're making. And then we have header lines that can follow that. And there can be a from field, which might have like an email address. There could be a user agent, which identifies the kind of browser you're using. There could be the host name that you're requesting data for. So these are header lines. And you'll notice that HTTP 1.0 defines 16 of these possible header lines, but none of them are really required. In other words, the header lines are completely optional on an HTTP 1.0 request. You could just say, get this thing, blank line by itself, and then get the response. And in HTTP 1.1 and later, it defines 46 potential header lines. And notice they're in the form of a key, a colon, and then a value. They're all in that form. But only host is required. And the reason that host became required later was that allowed for virtual hosting on one server. So in other words, you could have one server that says, maybe you have like get index.html from this domain, or get index.html from this other domain. So it allowed you to have one server serving web pages for multiple domains that were all still separated. And then with HTTP 1.1 and later, it requires you to have that host field, the host header. And then we have the blank line by itself. And then usually on a GET request like this, the message body would be empty. There wouldn't be anything after the blank line by itself. But in other methods like POST, for example, that's sending data to the server. Like when you upload a file to something, or you fill out some kind of form and then post it to send data to it, there'd be a message body that would follow that. Okay, well, let's look at the response. So the response has an initial line, which starts with a version. And then there's a status code, and then there's a reason, like a human readable interpretation of this status code. So in other words, this is the text version of what the status code is. And then the HTTP response can also have header lines, which it can tell us what the server was, what the when that thing we're asking for was last modified. It could tell you the content type and the content length. And then again, the blank line by itself, carriage return line feed, and then the message body that goes with the data from up here. And it goes with that response. Now, sometimes the message body might be blank. For example, if we get a different initial line here, or a different status code that instead of saying OK, would say 404 not found, then the message body that goes with that could be blank. It could just give us the 404. Okay, now the status codes themselves, they're all 3-digit codes, and they look like this. The first digit indicates kind of the classification or the type of category of the error. So 1 XX is an informational message, 2 is a success, 3 is a redirect to another URL, 4 is some sort of error on behalf of the client's request, a 5 is an error on behalf of the server. And some common ones that you're probably used to, 200 OK is one we just saw. Notice that's a success. 200 is success. 404 is not found. That would be an error on the client's part. Notice it's the client's fault for asking for something that didn't exist. 301 moved permanently. 302 moved temporarily. 500 server error. But the other digits determine the specific error of the category of these categories that we have here. And every time you get a response from a request, it's going to have one of these codes because that first line has to be there. Now, back here, we had that get that we looked at, but there are other message types. There's get, which basically gets a web page, a file, or some other resource. Could be a PDF, could be anything. That's typically what's used when you look at a web page is get. There's another thing that works like get, but it's called head, where it gets only the response header without the data that goes with it. So for example, we would only get the header, the initial line, and the header lines, and the blank carriage return line feed, and this would be zeroed out. And you might think, well, why would we ever want to do that? Well, notice that part of what this can return is the content length, the type, and the last time it was modified. So rather than getting the entire page again, you could say, when was this last modified? Okay, I was there when I saw that modification. So think about something like the Google, where it has to spider across the internet and update keywords and search terms. Well, they don't want to have to redo everything. So you could connect, look at the last modified and say, okay, how I have it indexed is up to date. I don't need to get this again because I already had it on that date. And so that's one of the uses for that. There might be other uses as well, like finding out how large some file is before you actually allocate the memory or do something with it. But head works just like get, but only gets the response header that would have gone with the request and not the actual data. Post is a way to send data to the server from the client. That's usually data sent from a script or program that are sent to a script or program on the server side. Maybe you're posting things into a database, you're updating some information in some database. And then Like post, there's also put, where data is sent to the server to replace some resource on the server side with data that gets sent. And put is different than post. Post is usually the data is going to some program or some script that's running on the server. Put is the idea behind put was almost like file transfer, where you're uploading some document over the top of some document that already exists. And you can't really just arbitrarily do that. The server has to be set up to handle put requests in the spot. So you can't just like replace Google's homepage or replace the content of something unless they have that enabled. And then delete allows you to remove resources from a website. And again, permissions generally prevent that, but you could set up a website that allows things to be put and things to be deleted and so forth. Okay, now we talked about some of the differences between HTTP 1.0 and 1.1. Another difference between 1.0 and 1.1 is the ability to have these chunked encodings on responses. And we're going to spend a little bit of time looking at that. Okay, so in looking at these chunked responses, the advantage for chunked encoding is that it allows the server to maintain some persistent connection for dynamically generated content. In other words, you could have, rather than having to receive the entire page and then render the entire page, you could start rendering it as you're still receiving other parts of it. And it also allows you to have that, maintain that connection to the server and get, for example, the web page part first, and then go back and get icons that get put on their images, go back and get CSS that goes with parts of the web page, go back and get some JavaScript that gets downloaded, whatever. But essentially it allows streaming of content as chunks, and then explicitly when you're finally done sending the chunks saying, okay, that's the end of everything. So it allows you to have a persistent connection that multiple data items come through as these chunks. So chunked encoding also allows the sender to send additional header fields after the message body. And that could be important where some case of a field isn't known until the content's been dynamically produced. And one example, if the content of the message has to be digitally signed without chunked encoding, the sender would have to buffer the content until it was complete and then calculate the field value and then send it and then send the content. Where this allows them to start sending the content, which could be dynamically generated, calculating some sort of check value, and then once the stuff is complete, say, okay, here's a check value that goes with that. Now, the way the chunked encoding works is like this. So it starts off with the header, including the line, and this is one of those header lines with key value paired, transfer encoding, :space, chunked. And what that means is for the rest of the transfer, once we get to the message body, it's going to have this chunked format. And that means that each chunk has a blank line, as there usually is before the message body, but then a line that has the size in a hexadecimal representation that specifies the number of bytes. And that's going to end with a semicolon and then another carriage return line feed. And then the data is going to then be sent after that. And then at the end of that, we're going to have this blank carriage return line feed by itself, again, as we did up here. And if there's another chunk, we'll get another hexadecimal size number ending with semicolon carriage return line feed, and then that much data, and then a carriage return line feed. And if there's another chunk, we get another line with that, and so forth. So that allows us to have numerous chunks come through. And that last chunk is going to be a blank line followed by a line with a size still, but that size would be 0 for the last one. And then after that last size, there can be additional headers, and they have the same form as the header lines at the top. In other words, key, value in a text format. And then the entire message ends with just a blank line by itself. Okay, so the idea here is we're going to spend a little time writing a web server. And when you visit web pages and go places and you go to Reddit and stuff comes up on the screen, and you go to Google and stuff comes up and you type in a search and it takes that search term and it gives you the responses, That might seem like magic, but it's really just an HTTP program, similar to what we wrote before. So we're going to write a simple one of those and look at a simple one of those today. And so we're going to take a look at how, rather than writing it live to keep the lecture short, I'm just going to show you the code and go through and explain it. And then we're going to run it and look at it in action. But the idea here is writing a web server isn't really any more complicated than the other TCPIP program that we wrote for the last lab. It basically just needs to read the request, the HTTP request, and then create a response, and then send the response. That's it. So on the server side, it's going to look like this. Open a socket, bind the socket to the local address, listen on the socket, accept a connection, and then once the connection comes in, we basically receive the HTTP request using receive. We then look at that request and form a response, and then we send an HTTP response using send, and then we're done. We shut down the connection, then loop back up to accept another one. And when you're interacting with a web server on the internet, this is essentially what you're doing. They have a program on their end that's doing this kind of thing, and you have a program on your browser that's making a connection, sending a request, getting a response, drawing it on the screen. So this is all stuff we've seen before. Socket, bind, listen, accept, receive, send, shut down. That's all stuff we've seen before. Okay, so let's look at the code for a simple web server, and then we're going to run it. We're going to test it with a web browser. So for our web server, let's go and just bring up the code. So give me a second to bring that code up, and then I'll walk you through it. So bear with me for a minute here while I bring that up. And I'm working on it here. Hold on. Okay, let me switch this over so you can see this code. And this is a really simple server version that I'm just going to kind of scroll down through. And this, put that where you can see it. Let me zoom in just a little bit here. Okay, so the idea here is, first off, notice the things that I imported, and this is written in C, like our previous version was. And so you could actually compile this and run this in Code Blocks or Visual Studio or whatever. But notice that this is a Windows version. If you are compiling this for Linux or some other Unix-based operating system, then we wouldn't be using WinSock. We'd have to do things a little bit differently. So watch the previous lecture if you are on one of those other systems. But there's just a few differences. The concepts are the same. For example, if you're doing this in Linux or Unix, you don't need this WSA startup thing. You get rid of that. Instead of WinSock, you would import the other header files for inet.h from where it lives, and so forth. But the overall concept is the same whether you're writing this for Windows or whether you're writing it for a Unix-based operating system or some other operating system. The sockets are still going to pretty much work the same. And it would also be the same if you're in other programming languages. Since other programming languages have adopted, for example, Python, their socket module in Python, it pretty much follows the same sequence of things that you'd have to do. It'd be a little bit less detail we'd have to worry about in the Python version, but it's the same thing. We'd still have to bind or create a socket. We'd have to bind the socket. We'd have to listen on the socket. We'd have to accept connections. Once the connection's made, we would have to respond to that. But we're going to focus on the C one since that's a little more complicated. So let's go through this. So first off, we import what we need imported, and then I'm defining the port that the server is going to listen on. Now I'm not going to use port 80, the typical HTTP port. I'm going to use 5454. And notice that's not hex. That's a decimal 5454. And the first thing we need to do is I've declared the variables at the top here. And you'll notice what I did here is I have my two sockets, S, which is my primary listening socket, and then this new _s, which is going to be the socket that I'm going to be performing the communication on after I receive a connection. And then I have some address structures that I have, one for my address that I'm going to use for bind, and one for the client address. When somebody connects, I'm going to get their address connected to me. And that's an important thing for you to realize as well. When you connect to a web server, like all TCPIP programming systems, they have your IP address when you connect to that. Now, the client address size is a variable that's used to fill in the size of this. That's part of how connect actually works. The receive size is going to be how much data we're going to receive from the client. And then this client request with this request size thing here, that is, and actually I'm not even sure where that is defined, which is weird. All right, I might need to make some changes to this. So yeah, let me pound to find that. Let's just do 2K worth there. And then we have this character pointer to the response that we're going to create. Okay, so let's go down through here. So this first part just initializes WinSock. We do that, which is the Windows socket DLL essentially. So we just do WSA startup. We pass in the address of that WSA variable up here, which gets filled in with that the WinSock handle for when that gets created. If that fails, if we fail to start up WinSock, then we print out the error message like this. If we make it past this, we've initialized WinSock. And now that it's been initialized, the next thing we're going to do is we're going to create a socket. So we do that by calling the socket function. And notice for HTTP, it needs to be a internet socket, AF_INET, and it needs to be sock_stream. In other words, it's a TCP connection, a streamed connection that's going to verify the integrity and the sequencing of the message. So we do sock_stream. So once that completes, it gives us a socket. If it succeeds, then we make it past this. If it fails, then we put out an error message saying, hey, I couldn't make a socket, and here's the error code why. So if we made it to here, the socket's been created, and now we're ready to actually start listening on a server. So here, we need to, before we do that, we need to bind. Which is going to happen down here. But before we do anything else, notice that we set the address. We have this SIN family AF_INET. We have our server port. We use the host to network short function, htons, to convert that into the correct network byte order. And again, that's for cross-platform support. That because some systems are big endian, most significant byte, least significant byte. Some of them are little endian, least significant byte, most significant byte. It's important that we have that 16 or that port number, which is a 16-bit number. It's important that we put that in the right way. So this host to network short makes sure that it's universally done on all systems. In other words, we get the right port number that we're looking for. So you should always use that function when setting the port. Now, after we have that set up, now we're ready to actually perform the bind. I have one additional check here that makes sure that the address isn't none for this, but we just set it there. And I have some stuff commented out here that's another way to set the that address using this inet pton function, which I commented that out and did it more the old-fashioned way, the manual way of doing it. But if you want to look at how you would do that another way, you can set the address using a string like that, rather than using the inet addr function that we had up here. I have that code in there as well. So note that I believe in Visual Studio it complains about using the inet addr and it wants to use the pton function. So here's the way you would use that here in these comments. All right, anyway, We then, after we've done that, we bind. So we call bind on our primary listening socket. We pass in the address that we just filled in up here, that's address structure, and the size of the address structure. And if that succeeds, we have now bound to that socket. If that fails, we get an error message printed out. And that error message might be something's already bound to that socket, or that's a socket you don't have permission to. There could be other reasons for it not binding. All sockets are currently in use. But if we make it to this line right here, to line 55, we are now bound to that socket. But we're not listening on it yet. So that's the next thing we do, is we listen on it. And this is, remember, this is the backlog. I'm using this SO max con thing here, which is defined up there. But if we wanted to, we could put in our backlog of 10 or whatever we wanted here for how many that it's allowed to listen on. So now we're listening on, if we make it past this, we're now listening. And if we made it past that and we're now listening, then the next thing we want to do is accept. So the first thing we do before we accept is we need to set this client address size to the size of that structure. So we set that variable up, and then we call accept connections on the socket we're listening on. And then we say, and here's the address of the structure that I want you to fill in with the address of whoever connected to us. And then here's the size of that structure, which we set up here. If we make it past this line, then somebody has connected to us, and now we're ready to receive their request. So to receive their request, we basically just do a receive. Here I put request size, which is the maximum size of that buffer that we created up here. So 2048, that is going to ensure that we never go off the end of that buffer we've set up. So that request is going to come in. We are going to fill it into that buffer, the client request buffer, which remember that was, if we look up here, that was just this array. It's an array of bytes. So if we make it past this line, we now have received the data, and we know how much data we actually received. We have the size of it. And now we're ready to send a response. And in my case, notice I'm not even looking at the request. In a normal web server, we'd look at what the request is. We'd say, okay, they want this file. I'll go find that file. I'll open it, and I'll send the contents of the file back. In this case, I'm just sending back a static response. And in this case, I'm just sending out kind of my response. So notice what I'm doing. Here's the initial line right here. HTTP 1.1, 200, OK. I'm saying, OK, I got your request. And then on the next line, here's the header, content type, text HTML. And there's the /r/n that goes with that, carriage return line feed that goes with that. Here's the blank line by itself. And if you remember, after the blank line, that means that the header is done. And now I have the message body, which in this case, I'm just saying, hello world is what I'm sending back. And then I'm doing the send on that. So I'm sending that response with that length. Notice I did string length +1 to also give it the pass the null character along. And then I've got that send now completed, going with this response that was a request that came in. So they sent the request. No matter what request they sent, we're going to say, OK, 200, OK, hello world in this thing, this heading of type 1. And then after that, we're going to close the new socket, which was the one that was returned by accept. And remember, the reason there's a new socket there that gets created from the listening socket. If you go back and look at the accept man page from a couple lectures ago, accept duplicates all of the properties of the listening socket, and the accepted connection happens on that. So think of like that. You call in the main number of a phone line, it rolls over to some other receptionist that handles that, which frees the main line for having another call come in and be handled. So in our case, this new socket, it works just like the original one, has all the same properties, but that frees up the existing one, the original one, to handle other incoming requests, which is why you can have websites handle a large volume of traffic without getting a busy signal, if you want to think of it as that. So in our case, though, I don't go back. And the one thing that's missing from this is a loop that goes back and receives more requests. In this case, for this simple example, after it sends the response, it closes both the socket that it communicated on. It also closes the listening socket, and then it does WSA cleanup and shuts everything down. And then it says everything's done, and then the program ends. All right, so let's go ahead and run this program and see it in action. So I have this compiled, so I'm going to switch over, and we're actually going to run that. So here I compiled it earlier, so I have the simple http server.exe. I'm going to double click it, and notice it ran, and notice that it was successful all up here. Initialized WinSock, it created the socket, it bound the socket, and now it's listening. So now it's waiting for an incoming connection. So let's give it that incoming connection. And notice, remember, this was on the local host. So let me bring up a web browser to connect to that here. So let me pull this tab over where you can see it. Okay, so here's this web browser. And you might ask the question, like, well, how do you go to that? Well, the way you go to that is up here in the URL, I'm going to put in localhost 127.0.0.1. And if I hit enter there, that should be trying to connect to the local host. And notice it says it can't be reached. Well, why can't it be reached when I have my web server running? Right here, let me make this smaller so you can see both of these at the same time. Move this over where you can see both of them at the same time. So the question is, why wasn't this able to reach that if that was listening? And the answer was, remember that I used that port in my source code. Let me switch back to that. I use this port 5454. But the default port for HTTP was not 5454. It was 80. So we need to have a way to say, I want you to go to this website but use port 5454. And the way that that's done in most web browsers is really easy. Just at the end of the address, we do :5454. And again, let me pull this up so you can see both of these at the same time. And now I'm going to hit enter on that. And notice that that ran, and then notice my server closed because I told it to. So there's my example. It pulled that up and rendered that. So and the cool thing about this is if you bound this to some address of some other server, you could get this message to pop up. Now, if I right click on this and say view page source, notice there's the message that was in my source code right here. There's the message body that came up. Notice that viewing the source does not show the headers up here because those aren't part of the message body. Those are the part of the header that would have this stuff in it. But here's the message body. It looks like, after the blank line by itself, it looks like this. And you'll notice there it is showing up in the browser. And there it is rendered in the browser. Now let's make, I want to make a couple changes to this code and recompile it just to add a little bit of dynamic content to this. So, and this is going to help you with the lab that's going to be posted today, which we will take a look at here in a second. But let me pause this for a second. Let me get this code into an IDE where I can compile it. So give me just a second here and I'll be right back. Okay, now what I'm going to do to write this code is I'm just going to use code blocks since that's free and cross-platform. You could also write this in Visual Studio or something else. So I'm going to go and just start up an instance of code blocks here. And we're going to do this program in that really quickly. And I'm just going to paste my source code from the other program into this. Okay, so as a quick reminder, here's the program that we had before, my example code. I'm just going to do a Control A on that, Control C. I'll move that off the screen like that. And now in here, back to code blocks. What I'm going to do in code blocks now is I'm just going to create a new project. So I'm going to say File, New. And we could do an empty file and add stuff. I'm just going to use their wizard. And I'm just going to make a console application, which really all that does is just make a hello world skeleton for us. So we could probably do without that. I'm going to do it in just straight C. And here I'm going to call it web server underscore example. And if you want to follow along, you could do this as well. And I was going to say finish. And notice that that's going to create my project under sources. It's going to have main. And there's my main program. I'm going to replace that with the thing I copied from earlier. So Control V. So there's all the code that I had from earlier that I brought up. Now, one of the things about this, though, is when we go to compile this and run it, it'll compile as is. But we're using this WinSock library. So we need to tell the linker about that. And let me show you what happens if we don't tell the linker about that. So let's just go and try to compile and run this. And here, I'll zoom in a little bit on the code so you can see it a little better. But if I just try to compile and run this, notice I get a bunch of undefined references here to this WSA startup socket. So all of those functions, it says it's an undefined reference. And those are linker errors. So the compiler, it compiled fine, but it couldn't link to these because the linker doesn't know where that library is. So we need to add that. So to add that to your project to get this working, go to Project, go to Build Options, and then under here, go to Linker Settings, and here there's a set of link libraries. And notice that none of them, there's no libraries in there. So we're going to add one. And if you are in code blocks, then I think I accidentally closed that. Clicked in the wrong spot. Hold on. Let me go back to that. So Project, Build Options, Linker Settings, Add. Okay. Now it's asking me to put in the file that I want there. Now we need to tell it that we want to link to the WinSock library. And under this min-gw build, whatever that is in Windows, that's going to be lib, because it's a library, wsock, which is WinSock 32.a. And .a is the kind of the library format for things. So lib, so library WinSock 32.a. So we click OK. Now that's in our link libraries list. We'll say OK. And now let's rebuild and try again. And now you notice it ran. And there's my code. And if I go back to my web browser, which should still be up somewhere here. Oh, I may have closed it. Here, let me make a new tab and we can go to it again. Oops. That's not what I wanted to do. So let's go to, put that there, right there. And let's go to that. Here, let's make this a little smaller. So we can see those side by side again. And let's do, nope, not there. Up, nope. Yep, up here. So 127.0.0.1, 54. And there you'll notice the program then finished, cleaned up, closed, and then here's the hello world. Now, a couple changes I want to make to this code quickly. So I'll go ahead and close this down. But one of the things I want to do is, what if I want to get something a little more interesting to happen here? So the first thing we might say is, well, what if I wanted to serve this in a loop? So let's add a loop around this. So the place I want to add a loop is going to be, we don't want to listen again. We don't want to bind again. We don't want to loop around the whole thing. We just want a loop around the part that accepts the connection and then receives the response and request. So here's where the top of the loop is going to be. And I'm going to add a print statement here. So printf, I'm going to say waiting to accept connection. And I'm going to put a loop around all this stuff here. So I'm just going to say while 1. And then I'm going to indent all of the stuff here up to that one. And I'm going to put my closed curly brace right there. So in other words, notice what I'm doing. I'm accepting a connection. I'm receiving the request, sending the response, and then closing the new socket, but not closing the listening socket. And notice that the way this is set up right now, this is never going to get out of here. So it's going to run forever. We're always going to have the server running unless we kill the process. But let's go ahead and run it and see. Now we can receive more than one request. So there it is running. Move that over here. Let's go back to our web browser. And now if I hit refresh, I get hello world. Notice it accepted the connection. We hit refresh again, and so forth. And now I'm serving this multiple times. Now, one thing that I'm going to do is, what if I want this content to be dynamic? So how can I make this content dynamic? Well, let's go back and look at this. So here, here's this response that I'm sending. But let's make it so this response changes slightly each time. So the way I'm going to do that is, rather than always saying hello world, I'm going to make a web page that just gives me a counter. So I'm going to, before this loop, I'm going to make a variable that's going to be my count. So here I'm going to say int count. I'll start it at 0. And then down here in my code, we are going to say, down here where we're making the message, I want to insert my count in here in some way. And I'm going to do that with a function called sprintf. So I'm going to comment out this line. And I'm going to say sprintf. And the way that works is we put in our destination, which is going to be response, that same response buffer we had before. And then here, I'm going to have my format string, which is going to be actually all of the same stuff we had before from here. I'm going to paste that in there. But the one difference I'm going to make is, rather than putting hello world in here, I'm going to say count %d. And then here, I'm going to plug in my count variable. And this works just like printf, but rather than printing to the console, it's printing into this string. So that number is now going to get stuck into where it did say hello world before. All right, so let's compile this and see if it works. Then obviously we send our response. So let's compile this and see it works. We got to close the old one. Let me just kill that. And now let's come over here, build this and run it. And there it is running. Let me move that over. Let's go back to our browser and hit refresh, which, here, what happened there? Okay, so that died for some reason. So we crashed that for some reason. Let's try again here. I don't know what happened there. Oh, I know what happened. Response is a character pointer. We don't have allocated data, so we need to make that a buffer. So let's let's do out buffer. Well, we must make 2048 bytes of that. And now, rather than sending that as a response, which the code is now a little bit out of sync, but let's do out buffer, and here out buffer, and then over here out buffer. You know what? There's an easier way to do this. Here's what I'm going to do. I'm going to point that pointer at out buffer. So I'm just going to add this line up here. I'm going to say hey, set the response pointer. So it's pointing at the that buffer location of memory. So when this gets stuck in there, it's going to go into that buffer without us having to change it in all those places, which I guess I was almost done with it. But all right, so we'll run that. There it is running. Now let's go back to our browser. And let's hit refresh. And now notice count 0. Notice I hit refresh. Okay, now you might say, well, why is count not incrementing? This should be increasing. And it's not. Now, there's a reason for that. And that's because one of the things you'll notice is here, let me, if you come and look at this area down here, when I hit refresh, you'll notice that this happens more than once. And the reason this is not incrementing, well, is pretty easy to understand. We never incremented our count over here. But there's another thing that can happen too with caching. But let's go ahead and just increment that count. So let's do that back in our code. We'll just do it after we send this one. We'll do count plus plus. That's a pretty amateur mistake that I made. All right, let's try again. Okay, so we built that and we ran it. There's our web server running. Move it over here. And then let's go back to our browser, hit refresh, 0, 2, 4. And you might say, well, why is it counting by 2s? Why isn't it counting by 1 every time? And so to get to the bottom of that, like we only have it incrementing by 1. Why does it go 54, 56, 58? And another thing you might notice is over here on this end. Let me kill this and then rerun it. And you'll see something interesting that happens here. Oops. You'll see something interesting that happens. Notice I don't have any connection requests coming in right now. But when I hit refresh, connection accepted, waiting, connection accepted, waiting. Why did it happen twice there? Why did I have 2 connections get accepted when I only hit refresh once? And that is why this is counting by 2s. And the reason for that is how the browser is actually performing this connection. So let's figure out what the browser is actually sending over to here. On the server, let's print out what the request that's actually coming in is. So remember that when we get this request, we're receiving that. Let's print out what the request is here. So let's do printf. We'll say request from browser. And then I'm just going to do a %s here, \n. So I'm just going to print out what the request is. And then here, the request is coming into the client underscore request. So we'll just print out what that is. So let's come over here. Let's kill this. Let's rebuild this and run it. All right, there it is running. Let's go back to the browser. Let's hit refresh. All right, so here's what the request looked like that came in. Waiting for connection, connection accepted, request from browser, get favicon.ico HTTP 1.1. Now, you'll notice that the reason why we got that request coming in twice is it tried to get this favicon.ico thing as part of what it tried to get when we did the refresh. So not only did it try to get the URL itself, so notice here's the get slash, which is that. Let's get the root page. But then it also then, after that connection, it connected again and said, I also want to get the icon that goes with it. And you might say, well, what are those icons? Those are the things that show up in your browser up here. And part of what the browser is doing is say, hey, not only do I want to get the page content, but give me the icon that goes with that page so I can make it show up. And so when you look at, have a bunch of web pages open, like here, let me pull this over. Like, for example, here's a bunch of web pages. Notice these all have these little icons associated with them along the top to help you identify which one's which. That's where that icon comes from, is that secondary request. So if we wanted to, we could send along or process this thing, and if it's get slash, we only process that when it's a get with a slash in it. We don't process it when it's got something other than that. Or we could say when I get the favorite icon, when I get slash favicon.ico, I send the binary image of what makes up that icon, and then it would show up in the browser up here at the top rather than that. But let's add one thing to our code to filter out so we only respond when we have a get space /. That's the only time we're going to send that response back. Or at least that's the only time we're going to handle that response the way we're handling it now. Okay, so let's look at that. So up here we have the request. We're printing it out there. So that's where we can decide whether you want to increment this or not. So what I'm going to do is I'm just going to add an if statement here that looks at that. I'm going to say if, and I'm going to do a string compare using strncmp. And if you remember how that works, we give it the two strings we want to compare. I'm going to say client request, and I'm going to compare that with the string for the thing that I want to match. If you remember what that is, it's just going to be a get space / space. So 1, 2, 3, 4, 5, those 6 characters. So here what I'm going to compare with is going to be a get space / space. And strncmp lets me specify the count, the max count. In this case, I'm just going to put 6. So 1, 2, 3, 4, 5, 6. So I'm going to make sure I match all of that. I'm not going to care about the version at the end of that. But if I see those two things match, and they match when this is 0. So if those two things match each other, then I'm going to send this response. Oops. Tab that over. Now let's see what happens. So let's go ahead and stop this. Let's rebuild this and run it. And there it is running. Let's go back to our browser. Let's hit F5. There's 0. There's 1. There's 2. There's 3. There's 4. So now we're ignoring the one that has the fav icon that goes with this page. So now you can see dynamic content coming up here in the page, and the server is serving a page, listening for the next one. And so forth. All right, so take a quick look back at that code one more time here. Let's close those out. And one other thing is this, here, let me bring that browser window back up for a second here. I want to show you one last thing with that. So one last thing with this browser window that I want to show you. Let's try that one more time. Let's do 127.00. Let's go back to that again. Notice that it remembered the count. It's not per browser window. So if I open up another one, that count is being held in the server, not as JavaScript inside of this window or something like that. It's not client side. That's server side data that's being put up on here. That's being exported up to there. So we've essentially made like a web counter, a page view counter, which used to be things that were on web pages. I don't think anybody really does that anymore because it's stupid, but we do. Okay, so let's go back to the presentation for just a second, and then let's take a quick look at the new lab assignment. And realistically, Internet of Things, you have some device that connects to the web, and you can log in and look at your security system or your webcam or something like that. All those systems are kind of similar to how this code is here. There's just running a web server. They're just allowing a connection, fielding a request, sending a response, and so forth. And if you wanted to, you could add other options to this that rather than just looking for parsing this and looking for just the get /, you could look for other things. So you could parse out the file they want and serve them the file, send them the file. You could parse out the really whatever you want. And actually, we've been going on for an hour today, so I think what I'll do today is I'll leave this here, and then next class I'll post the assignment and go over that, because I really didn't want to go over an hour today on the lecture. So I think I'll go and stop here. Let's go back to the presentation for a second, and then we'll finish everything up. So back to the presentation. Oh, all right, where were we here? Okay, so we looked at the code, we ran it, we got that coming up. And one thing about writing web server, note that it would not be difficult to add dynamic content. We actually just did that in our example. Or to make that into a real server that parses out the URI part of the request, which, if you'll remember, is right here. So we just need to parse that out. And since this is based on spaces, you can basically just tokenize this and say, get the part after the first space and up to the second space. And then return the contents of that file if you have that file. If you don't have that file, then you could return 404 error. And that's essentially how all web servers work, that they all follow that process. And you could write full-blown web applications in the same way, that instead of talking to a browser, a request comes in, the server fields a request with a response, then the application actually uses that in some way to populate a database or show things on the screen or give options to interact with some IoT device, whatever. It's all built on that same socket technology like that. And that's it for everything for today. Like I said, next class we'll have a lab where you get to write your own web server. What I would encourage you to do after today's class, because you should still have some time remaining, since it's a 2-hour and 15-minute slot, we've only used an hour of that, is to get the sample code working that we had for this example here. Get something like that working, test it out, play around with it a little bit, because we're going to be doing a version of that for the next lab assignment, which I will post next class. All right, so that's it for today. Slightly over where I wanted to be time-wise, but not too far off. So everybody stay safe, and I'll see you next time. And next time we'll have a lab doing an HTTP lab like this. All right, see you guys next time.